Okay, can you see the slides? Okay, good. So yeah, in the last class we have discussed about direct band gap and indirect band gap, and we have seen how the band diagram or the band structure of semiconductor looks like, and we have also discussed on the examples of each group. And last time I left you with a question as well, right? So we have discussed that silicon is an indirect band gap semiconductor, and therefore silicon cannot emit light. And direct band gap semiconductors like gallium arsenide, indium phosphide, for example, gallium nitride, they are all direct band gap semiconductors and they can emit light. So it's not happening in silicon because of its indirect band gap nature. However, in some conditions, silicon can be made, can be pushed, or can be created to emit light. So do you manage to find any of the answers of what are the conditions that allow silicon to emit light? Anyone would like to share? Anyone found anything? So silicon in its original form is an indirect band gap material. Therefore, it cannot emit light because upon when the electron drops from the conduction band to the valence band, the energy difference will be emitted as heat. But on the other hand, okay, I've got some answers here. Good. I'll go through later on. On the other hand, when direct band gap semiconductors like indium phosphide or gallium nitride, when the electron drops from conduction band to the valence band, the energy difference, or the EG, or the forbidden gap amount, is converted into light emission, right? However, in some condition, indirect band gap like silicon, it can also be made to emit light. So let's go through your findings we discussed. Okay, Juaria, alloyed with germanium, shaped in hexagonal structure. All right, so would you like to elaborate a little bit on that, Juaria? You can unmute yourself. Go ahead. Maybe you might want to describe a little bit or elaborate so that we can understand what's going on. Can you unmute yourself? Okay, all right. You found an article that said it's not easy, but it can be done, is it? Isn't it? A lot of germanium, is it? So that means the silicon is combined with germanium and shaped in hexagonal structure. Okay. So by this, do you mean that okay, silicon is in its own form is not hexagonal? So what is the original structure of silicon then if it's not hexagonal? Based on the article you read. Shaping the silicon in a hex, okay? So that means it's not in the hex structure to begin with, right? So what was the original structure then? Before hexagonal structure, before they are pushed or they are created, or they are made into hex structure with a germanium alloy. So you can share later on, yeah, from the article that you read. Okay. Any other answers? Arisha, alloyed. Okay, alloyed. Arisha, in your case, alloyed with germanium as well, or some other semiconductor material in order to be made to emit light. Oh, germanium as well. Okay. Alia, turn into more complex semiconductor. Okay, what do you mean, Alia? Could you please elaborate? You can unmute your mic. You can write it down here. Same article. Okay. Any other answers? When can silicon emit light? Faris, would you like to share your findings? Faris, you got something, right? You can unmute yourself and share. That's all right. Well, why not? That's okay. So you couldn't find anything on the experimental approach in order to turn it into direct band gap? Okay, Haziq. So what did he explain to you? You might want to share as well. You don't understand, okay. Okay. Then Faris, would you like to explain then? Haziq have read a nice article. Okay, Haziq, you got something, right? Don't you? So would you like to share a little bit on what you've read? So anyone working on silicon? Anyone's working on silicon nanoparticles or nanostructures for your FYP? Anyone? No. Anyone working with okay, not you. Okay, let me go through Arisha's comment. I think silicon has two FCC structure and shifted along diagonal with respect to each other. Okay, so Arisha, let me get your point correctly. So if this is the case, then FCC structure shifted along the diagonal with respect to each other. So then in that case, they can emit light or what? As a result of this, then would you like to add a little bit more? Haziq, nanocrystal. Okay, nanocrystal. Good answer. Yes, nanocrystals. Are you working on nanocrystals yourself on your FYP? Haziq? No. Okay. So if it's nanocrystal, then how does it emit light? If you've read anything on nanocrystal or anything related, would you like to add on a little bit on that? Nanocrystal, yes, they can. How? What's actually happening? Because we are interested in the physics or the underlying mechanism that governs the what we call the event, right? The happening of the emission of the light. Yes, it can, but anyone knows how does it lead to emission of light? So silicon in its current form, in its original form, is not in nanocrystal form. Yeah. It's okay. Let's discuss first for the next few minutes before we move into our topic. And then silicon is not in the nanocrystal form. Yeah, correct? If I give you a wafer, for example, I don't have a wafer now because I'm at my home. Kalau I bagi you wafer, so it's not in nanocrystal form. So Haziq, how do you then turn silicon into nanocrystals? Do you know any method, any technique? Maybe you've read through some of those. Okay, you can share if you have something. How do we then turn the silicon into a nanocrystal? My silicon, my question was, when can silicon emit light? So when means under what condition? So that means if I give you a wafer, a silicon wafer, one piece, so you cannot push it to emit light because it's indirect band gap in nature, right? So indirect band gap is poor at emitting light. So you can have some, but then it's very poor. So that's why it's not adopted for optoelectronic applications like LEDs and stuff. because you don't get to see the the light clearly, in contrast to other direct band gap materials like nitride or gallium arsenide, for example. Right, Mushfiq, your guess is once the electron leaves the valence and reaches the conduction, it emits extra energy. Okay, so leaving the valence and reaches the conduction band, it emits extra energy in the form of various radiation. Okay. So let's get this right. Okay, remember last time when I told you the transition can take place in two directions, right? So let's get this fundamental right first. So transition here means the electrons can either, hold on, let me approve your friend here coming into the session. Okay, the transition here means the electron can move from valence band to conduction band, so bottom to up. Okay, so in this case, to be able to move from valence band to conduction band, that means moving up vertically. Okay, we have the energy axis on the y-axis, and what we call space crystal momentum on the x-axis. To be able to move up, so the electron needs to absorb energy, so they need to be supplied with energy. So in this case, they do not emit energy. So moving up, they need to have energy, right? So they do not emit energy moving up. They can only emit energy moving down, right? So let's get the transition right. So transition number one is moving from valence band to conduction band. So if you want to climb something, if you want to climb a wall, for example, you have to be pushed, right? So you have to be supplied with an energy, with a certain amount of energy to be able to cross a fence, for example. Then only you can get to the other side of the area of the field, for example. So you need to be supplied. So in that case, you need to absorb the energy. You need to be supplied. So you don't emit energy yet. So that's the first transition going up. So the second transition is going down from conduction band to valence band, right? Going down. Going down, they emit the light, right? Because they go down, the energy difference between the edge of conduction band to the edge of valence band, which represents the band gap or the forbidden gap, will be emitted as light. Okay, so emission only happens when the electron drops from conduction band to valence band. In order for it to go up from valence band to conduction band, it needs to absorb, it needs to be supplied. So in this case, the question was on the second transition, not on the first one, right? So coming down. So to get back to your answer just now, no, because you're telling me the opposite direction, okay? So it has to go down. Rather, it's in the IR band. Still, the emission only happens in the second transition, coming down, not going up, right? Okay, Fatin, from the reverse bias, silicon PN junction under high electric field. Reverse bias silicon PN junction. Really? At which level? Fatin Nur Tahira. Reverse bias, no. But are you talking about certain value of reverse bias that can push the silicon into the right band gap? Fatin? Indirect, Mushfiq, indirect results in IR, aka heat direct is in visual spectrum. Yes, Mushfiq, but then the transition is about going down. It's not going up, right? So going from conduction band to valence band. Yes, okay. So if it is still an indirect band gap, then it will release heat, of course. But light will be emitted for direct band gap semiconductors. But the question is how do you push indirect band gap silicon to direct band gap silicon? So we've got just now. Okay, go ahead.
Doctor, by providing way more energy than it requires, then when it actually makes the transition, still will left with more energy that is not in IR band, rather it is in visual spectrum.
More energy, so that means you supply extra.
Extra, yes.
So in that case, you will end up with thermalization, because say your band gap, the band gap of silicon is 1.12, and you're supplying say 1.5, and what silicon needs is 1.1. So that means the extra 0.4 electron volt. Remember last time when I gave an example of you have a fuel for your car, but you want to get from my house to USM, but you can actually go further than that. But then uh, it goes further up into the conduction band, not just at the edge. So it can go up further into the conduction band, but then it will thermalize. All right, thermalize. It will still release the energy difference in terms of heat. Okay. Okay. So how do you then turn kinetic energy to emission? Will it be possible? Because the energy difference will be thermalized as heat. Okay.
Dr. by utilizing electron to matter interaction.
Okay, but then how?
So Bromsdahl effect. There is a Bromsdahl effect that can slow down. I forgot. I took the last semester. Bromsdahl effect can do this, right, doctor? It can slow down the electron and emit the rest of the energy.
As you mean X-ray? X-ray in electron beam system?
Yeah, doctor.
Yeah, but the emission level is not so high, right?
Yes,
Well, it makes
true.
sense. It makes sense. Yeah, it makes sense. Yes. Yeah, if
yes,
you're talking about, but you remember that the energy emitted is in the X-ray region.
Yes,
So
doctor. It is.
now we're talking about light emission in the visible.
So if the nucleus is not that powerful, then can it happen? Can it happen in because we take very heavy elements for the X-ray, right?
Yeah, exactly. I'm not sure whether it will still produce any X-ray at all if you reduce the strength, for example, in your case, or lower magnitude of the X-ray will be produced instead. I'm not sure, but X-ray will be produced during electron beam when you learn about electron beam evaporation system later on. So that Bremsstrahlung effect will be obtained, will be visible. It's just that it's not matched to the visible spectrum
Doctor,
that we're talking about. Yeah.
photoelectric effect.
Photoelectric. Okay, how do you relate that then?
Because it will knock out reverse of photoelectric effect, right?
Yeah, it's
And
reverse, right? It's reverse, right?
reverse of photoelectric effect.
Photoelectric is the absorption of.
Absorption.
Yes,
Yeah,
because if you're talking about photoelectric, then the transition will be the first transition going from valence band to conduction band, right?
Yes.
So anyone working on quantum dots or nanoparticles at all? No? In this team, in this group? Perhaps no. Okay, no, that's fine. Right. One other example would be in quantum dots. Right, let me show you an example. Let me just stop sharing and let me share a website instead. Okay, silicon. Okay, let me share the website. Yeah, hold on. Website. Okay. All right. Can you see the website now on the page? Yeah, is it visible? Yep. Can you see, right? Okay, good. So, well, this is among the, okay, this is only one example of many, many more examples. So you can use silicon in quantum dot. So silicon in its original form is in indirect bandgap material. It's an indirect bandgap semiconductor. But when you introduce quantum confinement, I think you have not learned yet the detail, because I think you're going to learn in 489 low dimensional structures. If you turn the silicon into quantum dot, or if you're changing the bulk silicon into quantum dot, you can actually emit some light from the silicon with even various colors. So you can see down here, I'm going to give you the link later on eLearn. So you can even alter the emission of light, which means alteration of the band gap of the quantum dots. So you can actually vary the size of the dot, for example, So on this website, if you are talking about larger dots, 5 to 6 nanometer, so very small, 5 to 6 nanometer, then you're gonna emit lower energy emission, typically in the red and oranges. And if you synthesize smaller dots in the range of 2 to 3 nanometer, you can emit higher energy light or shorter wavelength. So you can go into blue and violets, right? So it can be tailored, it can be modified according to the need of the application. So if anyone knows, for example, my colleague, Dr. Marzaini, so he's working on quantum dot based on different materials like zinc oxide or silicon. And this is what he's basically doing in his FYP and MSc and PhD as well, projects for the students. Anyone working with Dr. Marzaini? Haziq, who's your supervisor? Or engineering student, right? Because engineering FYP. Quantum confinement. So Haziq, in your case, who's your supervisor? Oh, Dr. Fairuz. So you're working on what? Spectroscopy? Yep. Okay, all right. So there are many more examples. So nanocrystals, just now, given by Haziq, sort of, right? Quantum dots and alloy, silicon to germanium. So if you look at Juaria, if you look at the article that you have mentioned just now, I believe they have said that they have not managed to get any emission yet from the alloy of silicon and germanium, even though they have managed to get a hexagonal structure at this point. But as of 2020, I think last year, they have not managed to get any emission yet. So, but they are confident that they'll get to it. Okay. So let me get back to the slide and continue. So I think you have got some ideas of the light emission from silicon. So it can be done, but it needs to be in different forms of semiconductor, if like, right? So it can be done. So I'll give you the link later on the references just now. So let's continue with conduction of carriers. So as a result of the band structure, we have covered a little bit on the conduction of carriers, which one is easily conductive and which one do not conduct and stuff like that. So let's go through 3 different types of band structures and what's the effect like in terms of the conductivity, electrical conductivity. So enormous variation in electrical conductivity of metals, semiconductors, and insulators can be explained in terms of the energy band. So if you look at the metals, for example, so we have discussed 2 cases of metals. The one in which we can see there's an overlap between conduction and valence band, but there's no actual bands exist because they are just overlapping with each other, and the carriers are there readily to conduct. And we have also seen another case where it's partially filled, as in sodium and potassium, for example, where they can also conduct because the valence band is not full, so it's not occupied. So metal in this case exhibit low resistivity or higher conductivity, as in the overlap band or partially filled band, right? So the uppermost electrons, hold on. Okay, the uppermost electrons in the partially filled band can move to the next higher available energy when they gain kinetic energy. For example, if you are supplied with electric field, okay? So in this case, electrons are free to move with only small amount of field because there are many unoccupied states close to the occupied states. So there are many unoccupied states close to the occupied states, therefore conduction is made easy. On the other hand, at the other end of the spectrum, so you have seen that insulators have very high resistivity, typically in the mega ohm, and therefore higher conductivity because it's just the inverse, right? So valence electron form strong bonds between neighboring atoms, and it's difficult to break, and we need high value of energy in order to push the valence electron to conduct. So have you guys seen the YouTube video I posted on Elon? The what is a semiconductor thing, the YouTube? when the guy tried to use silicon in different conditions to prove conduction, right? To alter the conductivity of the silicon. So if you watch the video, then you can see that silicon in its own in its original condition doesn't conduct, but once some heat is applied to the silicon, then we can get some thermal excitation of the valence electrons. So that means the valence electrons are thermally excited by the heat given to the system, or the system here is silicon. So they are excited, they are thermally excited into the conduction band and ready to conduct. And then okay, Faris watch, no, I think Haziq as well. Okay, Haziq bersama. And then you can see that the LEDs light up. So when the heat is applied to the silicon. On the other hand, the LED doesn't light up when the heat is not supplied in its original condition, right? So what happens in the video when he heated the glass? Haziq, did you watch? Apa jadi dekat glass tu? He supplied the very same energy, right? So he supplied the very same energy, but do you get to see any conduction? Do you see the LEDs light up at all? Faris? Haziq?
The glass ada tu.
Yeah. Glass tu conduct tak?
Glass tu tak.
Tak conduct, okay. Why is it so?
Because it doesn't have high heat conductivity.
Okay, so he supplied the heat to the silicon, and silicon stays in the connection and the LED lights up. So that means the silicon now conducts, right? So at the same time, he supplied the very same amount of energy to glass to replace silicon in the circuit, and then the result is the LED doesn't light up. So that means the glass remains as an insulator, isn't it? So apa maksudnya? What does it mean? How can it happens on silicon, conducts, but after the same heat, it doesn't conduct for insulator? It melts, but it doesn't conduct. What happens? Why does it melt? And why it doesn't conduct? It's melted already, but still doesn't conduct. What happens? What can you say about the energy supplied to the system?
I think it involves the band gap, the energy that is transferred to the balance to the
Glass?
in the balance band is not utilized enough by the carrier.
Right, the keyword is not enough, right?
Yes.
The keyword is not enough because if you look at the try to look at the band gap of the material. I think it's so big. It should be more than 5 eV at least. So that means even though your heat is strong enough to push silicon to conduction, but it doesn't manage to push glass to conduction because the glass is already melted by then, right? And there's still no conduction. So that means that we can demonstrate the amount of energy required in order to release the valence electron free from the valence band in order to push for conduction, and it's still not happening, right? So it's very interesting video, a simple demonstration, but if you can relate back to this principle, then well, you can explain very clearly already. Okay, you're interested to know why is it broken? Well, try to look for a reason why is it broken. What's the melting point of glass? Try to look into the melting point of glass and see what's the energy supplied by the heat and knocking out a valence electron, right? Okay, try to look into the melting point of the glass. How much is required to break a glass? And that is still not required not enough to push for conduction. So insulator is a band gap, it's a large band gap material. So electrons occupy all energy levels in the valence band, and all energy levels in the CB or conduction bands are empty, right? Okay, so although insulator has many vacant states in the CB, they can accept electrons, so it's still not possible to demonstrate any conduction, right? On the other hand, so we've discussed about one extreme, the metal. So we've discussed about another extreme, the insulator. So now we are sitting in between, in between the spectrum, where you can actually alter the conductivity of the material. So we call that semiconductor. And you can see that in the video I posted on eLearn last time, where you can heat the silicon to see conduction. The moment it's removed, and LED will dim out, right? So at T0, if you're talking about 0 Kelvin, then all electrons are in the valence band. Therefore, there are no conduction, right? There are no electrons in the conduction band, and therefore no conduction. So at this condition, silicon, if you talk about silicon, then it is a poor conductor at low temperature. So it's like frozen at that particular temperature. So at room temperature, room temperature is 300 Kelvin, so that's 300 K higher than 0, right? And under a normal atmospheres, so we know that the band gap of silicon is about 1.12 electron volt, and if you talk about gallium arsenide, it's 1.4. So since it stays at the room temperature, which is 300 K higher than 0 in the previous case, so we have got some thermal energy already, KT, at room temperature, right? So Boltzmann constant times the temperature, 300 Kelvin. So therefore, appreciable numbers of electrons from the valence band are excited into conduction band. So whether or not it's enough to light up certain system, then it depends on the input requirement of that particular device, right? But appreciable number of electrons are already ready in conduction band for conduction. So there are many empty states in the conduction band and a small applied potential. If you give some bias to the silicon, for example, or some external excitation, for example, so you can push for more electrons going into conduction band or being excited into conduction band for conduction. So therefore, you can actually modulate the conductivity of your semiconductor in this condition. So that's briefly how it looks like. We're going to see more and more later on. So let's see how temperature and band gap affects conductivity. Right, temperature dependence is the first one. So the temperature dependence of the energy band gap has been experimentally determined. Okay, you can look into this equation, and you can look into the table summarized the results of the experimental findings. So you can see that you can see from the table down here and also from the plot here. So the band gap is on the y-axis and the temperature is on the x-axis. So in this case, the experiment increased the temperature from say 100 Kelvin up to 1000 Kelvin and try to see what's the effects on the band gap of 3 different semiconductor materials: gallium arsenide, silicon, and also germanium, right? So the results are summarized in the table on the right. So let's look at silicon first before we look at others, because the trend will just follow as you can see on the chart here. So at 300 Kelvin at room temperature, silicon demonstrate 1.12. So you can see here 1.12 silicon, right in the middle here, 300 Kelvin between 1.1 to 1.2. And then when it's heated to 400 Kelvin, then it goes down to 1.09 electron volt. Just a small change, small reduction in the band gap. And if it's heated even further to 500 K, it goes down by another 0.03 electron volt to 1.06, and then so on. To exceed 600 Kelvin, it goes down by another 0.03 to 1.03 electron volt. So you can see pretty much the same trend on germanium and gallium arsenide with slightly different, gradient, let's say. So, but pretty much you can see the trend. So it decreases. Why? When it's heated, the interatomic spacing increases when the amplitude of the vibration. The moment you heat up the atoms, so they're going to vibrate. So hence the interatomic spacing between the atoms, the effective interatomic spacing, increases due to increased thermal energy. So this will result in a decrease in potential seen by electrons in the material, which reduces the EG, right? So on the other hand, if you talk about doping dependence, so if you talk about more and more doping, for example, if you increase, in this case, your doping, you increase from 1016, so you start off with 1016, to 10, 17, 18, 19, and 20. So you can see band gap also changes accordingly, but they just don't show up until 10 to the 18. So if you see, when you increase your band gap from 16 to 18, there's barely any change. Well, you can see a little change there from 0 down to minus 10, minus 20 milli electron volts. So that's very small. So electron volt divided by 1,000. So that's quite small, but you can see a more significant effect on the band gap reduction when you go past 10 to the 18 per cm cube. So that's governed by the equation given above. So from the trend, you can see that the band gap shrinks at higher doping levels. So we also call this as band gap shrinkage or band gap narrowing effect. Some even call this as BGN, band gap narrowing effect. BGN, band gap narrowing, or you can also say band gap shrinkage. So either one is fine. So it's referring to the same thing. But for example, if you look at silicon, the blue curve, so if you dope your silicon at 1 times 10 to the 19, so right here, so that means the reduction, if you compare to 10 to the 16, so we got the reduction of 70, 75 milli electron volt, more or less, right? So at this point, that's about, yeah, 0.075 electron volt or 75 milli electron volts. So that's the amount of reduction. Whether or not it's significant to the device, it depends on the device actually, because we don't have any blanket setting for the device. So some operate some layers in the device. We're going to see later on, if you talk about integrated circuit, they are talking about tens of different layers in the device in order to form the final functioning device. So you will also see that each layer may need different doping levels. Some may need intrinsic, some may need 1016, some may need 1019, some 1018. So there's no one answer for that. So it really depends on the requirement of every single layer in order to make the device functions correctly or properly, right? So at least now we know that if you dope at higher doping levels, so we'll suffer a little bit on the band gap shrinkage, which will affect the properties of your materials and your devices. Okay, yeah, that's all. Yes, that's all for today. What time is it now? 1:40, so a bit early, but that's fine. Okay, so I'll give you the link on the what I call it, the alloying just now, alloying mentioned by Juaria and few of you, and also nanocrystals and quantum dots formation and what makes the silicon emit in that sense, in those cases, right? In comparison to the bulk. So that's all for today. Any question? We're gonna continue to Fermi energy and density of states tomorrow. Oh, you're together in the room, huh? Haziq and Amirul, right? So your roommate? Okay, all right. I thought your brother or what? But I recognize the face. Okay, anyway. All right. So good. I'll see you tomorrow then. Tomorrow will be 10 a.m., right? 10 a.m. Okay, so I'll continue tomorrow at 10 a.m. Fermi energy and density of states. Okay, then bye-bye. Take care. Assalamualaikum and stay safe.